It's Maguraushe on the other side, and I think we have been on hold. Everyone was on hold, waiting for the way forward in as far as continuing with our module is concerned. Well, I tried to do. I tried multiple times. Trust me when I say I tried multiple times. If you ask me right now, I'm recording this around 4 a.m. because since Saturday I've been trying quite a lot of these applications, and unfortunately, most of them, should I say almost all of them, after doing the video presentation and trying to upload it, I discovered that the smallest I could get was around 170 something, which I believe is totally, it's way too big. Most of us won't be able to afford such data packages to download huge files. So I decided to just do to get another tutorial which will allow me to do the presentation, but at the same time, with audio, infusing my audio and the presentation. But unfortunately, you won't be able to see me, but it's okay, right? Because the issue here is not about seeing me, but about seeing action. So I said we need to appreciate quite a few things before we write our exams, right? So I'm going to be hammering on what I believe are fundamental areas which are critical for someone to achieve at least a pass on your IT 404 module. I'm sure you know you're going to be writing your exams end of this June, so we better be prepared. Otherwise, failure will be our common adjective. So we need to appreciate the concept called encryption, then describe the various, not the various, but rather the two types of encryption, that is symmetric and asymmetric. Then we do some calculations, right? Euclidean as well as the extended Euclidean algorithms. Why do we need to do these calculations? You discover that some authors tend to use the extended Euclidean as well as the Euclidean algorithms when they do the calculations for the commonly used asymmetric algorithm, which is the RSA. And all these things, if time permits, we need to do the discussions within the context of this lecture today. So encryption, one would ask, what is encryption? Encryption, we are basically looking at a technique which is used in computer security, whereby we try to hide the contents of a message, right? So that even if someone is to intercept the message, you cannot make sense of the message. How do you do it? You need to convert the original message or the plain text into a format that we call the ciphertext, or a text which is in a coded manner, right? Which makes it difficult for any person, a third-party person, the unintended recipient, to view and actually make sense out of the message. Then on the other end, it's still part of encryption. You need someone to convert back the message from the coded message, or from the coded format, from the ciphertext, back into the original format or the plain text, so that you'll be able to read the message. So for both encryption and decryption, one is going to require a key, which takes us to this question whereby someone will say, which keys are you going to be using? This is decided by the framework that you're following, whether it's symmetric or it's asymmetric. If it's symmetric, then you're going to be using one key for both encryption and decryption. So when you are encrypting, you use one key. This very key, you need to use it for decrypting, so that you'll be able to make sense out of the message. So basically, if you look at that scenario, you will discover that the key is supposed to be shared, because it's going to be used for both encryption and decryption. So that brings about, advantages like the method being simple as well as it being faster, right? Why? Because you're going to be using one key. But you mustn't negate the fact that you're using one key. Imagine someone intercepts the message and maybe you have access to the shared key. Then automatically the message is compromised. In other words, we are no longer secure because we know security allows for things like confidentiality, integrity and all those things. So if the message is intercepted, then the message is no longer confidential. It has been intercepted by a third party who is not the intended recipient, right? And of course, so for you to secure this crypto system, you need to have your key exchange in a very, very secure manner. So this is the essence of using one key for both encryption and decryption. But going forward, we also have another type of encryption, which we call the asymmetric one, whereby you are going to be using two keys for both encryption and decryption. What am I saying? I'm saying you need one key for encryption. Then you need another key for decryption. So you're going to be using two keys, the public key and the private key. Public key can be seen by anyone. Public key is the one which is going to be used for encryption. Then the private key is going to be used for decryption. But what you really need to understand here is when Alice intends to communicate with Bob, you've got your Alice who intends to communicate with Bob. Now, what has to happen is the recipient needs to generate both the keys, that is the private and the public. Then the recipient will send the public key to Alice, right? The public key is sent to Alice, but well, in some instances, you discover that the public key can be viewed by any third party. It doesn't matter because as long as you don't have this private key, you cannot decode this message. So of greater importance here is for you to know, to keep, let me put it that way, is for you to keep your private key in a secure manner so that no third party will be able to have access to it. Because this is the very key which you're going to use for deciphering, or should I say for decoding the message, right? So it's more secure. I think you can easily tell that we are using two keys. The public key can be compromised, but definitely nothing will ever happen to your private key as long as you keep it in a secure manner. Then we also have some form of authentication. You can ascertain the individual or the other party that you're communicating with, because you see, the only party which is supposed to make sense of the message is the one that I ought to talk to, right? So if I send a public key to Alice and I'm Bob, then after Alice sending a message to me, I'm Bob of course, then and I am able to decipher the message, then it definitely means that there is some form of authentication. We can ascertain the identities of the parties which are in the communicating channels. But of course, the issues to do with using one key for encryption, encryption, there is some mathematics involved, as well as, all these, I would rather call it the mathematical gymnastics involved. So you really need to be good. It's because the process itself seems complex. You're going to discover, because we need to discuss the RSA, like I indicated earlier on. So this is the long and short of how asymmetric encryption is done, because the first step is for the receiver to send a public key to the sender. The receiver is the one who, mind you, we said he's generating two keys here, the public key and the private key. So you need to give your key, the public key, to the sender, and the sender uses that very public key to do the process of encrypting the message, converting the message from plain text into a ciphertext. Once that is done, the message is sent, and on the other end, Bob, the receiver now, must then convert back the message using the private key. He is now using the private key to convert the ciphertext into plain text in a process called decryption. That is the long and short of doing this whole process. Now, this is more like a summary between our symmetric and asymmetric key cryptography, right? Of basic importance, I think, of greater importance is the fact that on symmetric, we're going to be using the same key, right? If you look at the keys, I think you can easily tell that we're using the same key for both encryption and decryption. But when it comes to asymmetric, you've got one key for encryption and you've got a totally different key for decryption, which we described earlier on. So, what are the tools that you need when you want to implement or to execute some form of cryptanalysis? You agree with me, definitely you need encrypted messages. Why? Because that is the message which you need to maybe convert back into plain text at the end. You also need to know the algorithm which is used. There are quite a lot of algorithms. There are very simple algorithms that we didn't do, that we are not going to discuss now, but I understand we did them. Things like the cipher algorithm, with the one-time pad, we've got the version rare, you've got the hell fence, you name them. They are all types of algorithms. Of course, I expect you to appreciate them, but I'm going to focus on those which will require some form of calculations because they are of greater importance. Once you start doing calculations in encryption, then you know I'm using an algorithm that is pure, that is sound, and that is more secure, right? Then, of course, one might need to intercept some form of plain text so that at least you can do some form of cryptanalysis. All these other things like mathematical and statistical tools, techniques, these are required when you want to do cryptography or cryptanalysis. You need to understand the properties of languages. You need computers. You need luck and ingenuity. You also need known data items or suspected to be in a ciphertext. Why? Because you need some form of a starting point when you want to crack a certain message, right? That's why we normally tell you that, okay, don't make things very, very obvious, like when you are coming up with your password for your email or for anything, right? Someone will just end up putting maybe their date of birth rather, or the name of their kids, or the name of their spouses, or their lovers, and etc. You're making it simple for these hackers to just come and pounce on you. Why can't you use words or use a combination of characters which makes it difficult for the hackers to have access to your system? But anyway, it loops back to our choices, isn't it? And then, how good can a crypto system be? This can be based on three metrics. The first one is to assess it based on its soundness in terms of the mathematics involved. If a crypto system is of sound mathematics, trust me, it's good, it's super, because you are making it difficult for the hacker to even have a successful attack on your system. Now, I know some of these algorithms are very, very difficult to implement, right? But do you know the person who is going to try to have access to your system is also using some sophisticated tools and equipment and machinery? And once they have everything in place, Don't make it don't make it very simple for them to have access to your information, to your precious information. So come up with a way of securing your system mathematically, right? Then if a system, or if an algorithm, or if a crypto system rather, has been analyzed by competent experts and the conclusion maybe was it's so sound, then we can say, no, this is also good. Why? Because these are experts in the field of cryptanalysis, right? They know every corner, every aspect of making an algorithm or making a system strong. So if they analyze it and they give it a green light, then definitely you're using a system which is waterproof, which is tight, which is sound rather. Then of course we also have a system that is continuously being used. In other words, we are having a system that is standing the test of time. Why is it standing the test of time? Because maybe people are trusting it. Maybe it's giving them the features and security that they so desire. So the system has stood the test of time and it's continuously being used, then automatically you can continue using or utilizing the system. Right. On our mathematical side of things, encryption, of course, it has some theoretical aspects, but you cannot ignore the gymnastics of doing some calculations here and there. Now, here is what we are going to be doing. We're going to be doing the calculations theoretically here, right? And I hope most of you are able to follow. I just hope so. Please forgive me, but I hope you'll be able to follow. Now, the first thing that we need to do is to calculate the GCD of a number. How do you calculate the GCD of a number? You know, when we talk about the GCD of a number, we're talking about the greatest common divisor of, let's say, two numbers. We've got 3, we've got 6. What is the greatest common divisor? It's a number that gets in, the greatest number between the two that can get into the two numbers without leaving a remainder. So that's the GCD. And how do you calculate the GCD? Like I indicated, you use the Euclidean algorithm, right? So you use it to calculate the GCD of two integers. Numbers are very, very important, especially in encryption, because like I said, you measure one of the metrics used to assess the strength of an algorithm of of a crypto system is to assess its mathematical soundness. So we really need to know the properties of numbers. We need to know integers. We need to know especially prime numbers, right? One will ask, why this sudden interest in numbers, right? Because we are going to be combining numbers when we do this encryption thing, right? So when you encrypt, we want to make it difficult for someone to assume that these are the numbers which are used for combining our key or for coming up with the key, right? You will appreciate it better later on. So let's continue. So the GCD of a number normally is denoted by the GCD, like this, the GCD of A and B. And you must know that your A and B are integer values. So the algorithm goes by, if your A is equal to 0, then the GCD of A and B is equal to B, since the GCD of, so in a nutshell, we are simply saying if you are looking for the GCD of A and B, you first of all get B sometimes with a remainder. So the GCD of A and B must be equal to B plus some remainder, right? There has to be a remainder somewhere. Now, this remainder, we're also going to use it as a factor. You continuously do this process to say the GCD of this is stipulated on this algorithm until such a time when your remainder is 0, right? When your remainder is 0, the big question now is, then what is the GCD? The GCD becomes the last non-zero number. So you continue doing this. The next thing you do, you are going to use these as two factors. Then you're going to get R plus another variable. You continue until you get a certain number plus your 0 as remainder. Then you take it as your GCD. But well, let's do some activity here. Let's try to calculate the GCD of 270 and 192. And this, like I indicated, this is the format that we use. Now, for status, sometimes you discover that you are being asked to calculate the GCD of 192 and 270. That being the case, you are allowed to swap, right? To swap positions. A is always supposed to be greater than your B. That is the case. A is always supposed to be greater than your B. So you can swap positions. That is if and only if your A seems to be smaller than B. Make sure that you swap positions and then treat the B as A going forward. Then we now have the GCD of 192 and 270 and 192. So how many times, please, we are worried about the remainder here, right? The quotient. So how many times does 192 get into 270 without leaving a remainder? Because our 192 is our B, right? 192 gets into 270, I think, 1 times. The remainder is 78. You write it that way, right? You write it that way. Then the next thing, we need to calculate the GCD of your 192 and your 78. Now this is a new scenario of which your A is now 192 and your B is 78. So 78 gets into 192 2 times. 2 times 78, you get your answer and you less it from 192. I'm sure you agree with me. You're going to get 36. Right? I hope everyone is following. Then we proceed. We now need to calculate for the GCD of 78 and 36 because these are our new term, our new values of A and B. So the GCD of 78 and 36 is equivalent to, how many times does 36 get into 78 without leaving a remainder? It gets there twice. And what is the product of 2 and 36? That's 72. 72 from 78, you get your 6, right? Then the next thing that you need to do is to calculate the GCD of 36 and 6. The GCD of 36 and 6 is equivalent to, how many times does 6 get into 36 without leaving a remainder? It gets there 6 times. What is the remainder? It's 0. We are done here because we managed to get to 0. So what is the GCD? We said is the last non-zero remainder. Is the last non-zero remainder. What is the last non-zero remainder? It's our 6 here. So the GCD of 270 and 192 is equal to 6. You will be done doing your Euclidean algorithm if you do it this way. All right? Then the extended Euclidean algorithm is basically an extension of the Euclidean algorithm. You first of all execute it using the Euclidean algorithm that we just discussed, but we now need 2 additional integers, right? When we're doing the Euclidean, mind you, we had A and B. Now we need to compute for additional integers, that is X and Y. And please note, these two values, normally they always have, opposite signs. If one is negative, then the other one definitely is positive. That is the norm between those two numbers. They are always like that. Now, we want to express it in the form ax plus by is equivalent to the GCD of A and B. This is what we want to do. Ax plus y being equivalent to the GCD of A and B, which you can, of course, represent using a variable like D. Right. This, like I indicated, is also very, very important for the crypto computations that we're going to do. But maybe I'll try to show you or to use a different way. But you are allowed to use the extended Euclidean algorithm for later computations. Okay, that's why we are doing it right now. So, what are the steps? Like I indicated, this process is 2 steps. Right? The first step is the one that we did, right? That is the Euclidean algorithm. Then the second one is the back substitution. You are going to be, after doing your Euclidean, right, like this, you then indicate your equations that this is 1, this is 2, this is 3. Then you do back substitution, making substitutions on your remainder. Let's see it. Right, we've got a question. Find 2 integers A and B such that your 1914A plus 899B is equivalent to the GCD of 1914 and 899. First of all, like I said, let's use the Euclidean algorithm. Let's do it first. First of all, we are calculating the GCD of 1914 and 899. If we had this question is the GCD of 899 and 1914, I am sure you now know you were going to swap positions, but because your A is always supposed to be greater than your B. But this is a normal case, so we need to calculate the GCD of 1914 and 899. How many times, this is your A, and the remainder, how many times does your 899 get into 1914? It gets there 2 times. Then you multiply 2 times 899, you get your product, right? We are saying 899 times 2, that's 1798. Then you subtract from 1914, you get your 116. True? Right? So this is your remainder, the first remainder. Then we label it equation 1. The second equation, we are now calculating or computing for the GCD of 899 and the remainder, which is 116. So your 116 becomes your B and your 899 now becomes your A. The GCD of 899 and 116. How many times does your 116 gets into 899? 899 over 116. 7 point something. So the whole number is 7. So you say 116 times 7, you get 812. Then 812 from 899, you get your 87 as your remainder, which is equation 2. Right? Then you continue. You now need the GCD of 116 and 87, right? And how many times does your 87 gets into 116? It gets there 1. And what is the difference between 116 and 87? It's 29, right? That's your remainder. And this is your equation 3, right? Then you now need to compute for the GCD of 87 and 29. How many times does 29 gets into 87? is 3. 3 times 29 is 87, so your remainder is 0. So we are done. So if it was the Euclidean algorithm, one would say the GCD of 1914 and 899 is equal to 29. If it was the Euclidean algorithm, you would be done. But we still have the second part of our extent. We need to implement the extension aspect. Now this is slightly tricky, but if you pay attention, I'm sure you'll be able to understand this. Now you take the last equation with a remainder, or the equation which is giving you the GCD. So you say in in 3, make 29 the subject of the formula. So if you make 29 the subject of the formula, I'm sure you agree with me that this whole function goes to the other side of the equation. Of greater importance here is for you to understand that this is a single function. It's just like saying 2a. Do you know you can write 2a as 2 times a, right? This is exactly the same. This is also the same here, 7 times 116. So your a is the variable, then the 2 is the coefficient. Your 87 is the variable, then 1 is the coefficient. Your 299 is the variable, then 2 is the coefficient. We need to put it that way. You don't evaluate here, right? So 29 is equivalent to 116 minus, you take this to the other side of the equation, it then inherits a negative sign. So minus 1 multiplied by, or you can use this sign. I normally prefer to use a star. Multiplied by 87. If you evaluate 116 minus 87, you get 29. So what are you doing? You don't evaluate because these are variables. But in any case, the reason why I'm saying if you evaluate, you get the same. You need to appreciate the concept of an equation. Left-hand side is equivalent to the right-hand side. Now proceeding. So this is what we have somewhere here, right? This is exactly what we have there. Then, you agree with me that this is the simplest form. If it's the simplest form, you go to the aspect was we do back substitution, right? I said back substitution, right? So you're doing backward substitution. Never mind the handwriting. That's not my handwriting, but you know it's always difficult to write using a what? Using a mouse. You can try it if you think you are better. Okay, so we now go to the next equation, which is now in 2, right? Let's make the remainder the subject of the formula. 87 is equal to, you take this to the other side of the equation, so 899 minus, by the way, 899 is also having its coefficient. If you are having a, what is the coefficient? It's 1. So it's 1 times 899, which is 899. 899 minus 7 by 116. That is my times, right? So this being the case, why can't we take this 87 and substitute it here? You know, issues to do with substitution, right? Why can't we take this 87, the equivalence of 87, the equivalence is this function, all right? And substitute it here. This is exactly what we did here, right? We are substituting 87 into our expression here. So you end up with your 29 being equal to 116 that we had there, this, plus minus, because this one, when it migrated to the other side of the equation, it changed the signs, isn't it? So we are adding, this is just the same, plus minus 899. What you need to note here is we are now substituting 87 with 899 minus 7 times 116. So actually we need a bigger bracket here, right? We need a bigger bracket because minus 1 is affecting everything. Minus 1 here is affecting our 87. 87, which is equivalent to our 899 minus 7 times 116, right? Then, you know, your O level will tell you that you need to clear the bracket. You simplify, isn't it? So, you're now saying 116, here, like I said, it's 1 times 116 plus minus 1 times 899. I'm sure you will get minus 1 times 899, right, as it is. Then minus and the minus will give you a plus. So this, the coefficient will be plus 7 times 116. Now we've got 116 here and another 116 here. So you add the coefficient. This is a plus 7. This is a plus 1. So you eventually get a plus 8 times 116, right? Like I said, this is one function. Please, I will continuously remind you. Then this negative 1 times 899 will just continue as it is, and you have minus 1 times 899, right? In that order. Then you try to there is no any further way of simplifying this. So what you do, you go forward again, upwards to equation 1. Right, the last expression which you are going to have must have the first two expressions which you were given, right? It must have the first two expressions which you were given, that is 1914 and 899. You need to see them on the last expression that you're going to have. So let's continue that way. Then we need to make 116 the subject of the formula. 116 is equal to, right, 1914 minus, because this is crossing over to the other side of the equation, isn't it? Minus 2, minus 2 times, what is that? It's 899. Okay, I was supposed to even say plus. It's the same anyway. For those who understand mathematics properly, 899. Then you close your bracket. Now, is it the case? Yes, that is the case. That is the case, yes. 116 is now the subject of the formula. So, where we see our 116, this was our simplified version, isn't it? We now need to come and substitute for 116 here with this whole expression. 1914 plus minus 2 times 2899. This is the same. Minus, you can put it there and you can have a positive there. It's still the same for those who understand mathematics. So, which I assume you do. Then we need to simplify this, right? If you simplify it, here it's gonna be minus 1 times 899. It will continue like that. Then here 8 is affecting everything inside our bracket. Are we together? 8 is affecting everything inside our bracket. So 8 times 1914, you get 8 times 1914, right? Then 8 times 2, you first of all deal with the coefficients. They give you minus 16, this and that. They give you minus 16. Then minus 16 times 899. But mind you, we had another coefficient for our 899 here, which is -1. So you deal with the coefficients only because you are adding or subtracting functions, like terms rather. You're adding or subtracting like terms. So you just deal with the coefficients. -1 minus 16, you get -17, right? So at the end of it, this is the simplified version of our expression. Now, how then do you know that this is the final thing? You will agree with me that if you have your let me write it, ax plus by, we said it's equivalent to the GCD of A and B. This is what we said when we started. So your expression now is now in the form of AX plus BY equal to the GCD. So we can automatically say, if we have got 8 times 1914 minus 17 times 899, then automatically what it means is the value of your A is this one, it's 8. The value of your B, the value of B is -17. So A is equal to 8, B is equal to -17. And you remember I said these two must have opposite signs, and this is conforming to that. So this is how you do your extended Euclidean algorithm. I hope you understand. I hope it's clear. If it's not clear, we'll find ways of diffusing that confusion. Now, the last thing that I want us to do, or that I want us to cover, is the RSA algorithm. The RSA basically was discovered by three prominent experts in the field of cryptography, right? We had Rivest, we had Shami, we had Alderman, right? These were the three guys who discovered the RSA, I think in 1977, right? If I'm not mistaken. And this was the first asymmetric. This was the first asymmetric algorithm to be designed, right? So they came up with a novel idea. They designed this algorithm. The three of them, they had to put their heads together, right? Now, of greater importance in appreciating the RSA is the fact that we're going to be using two keys. We're going to have a private key as well as the public key. You're going to use the public key for encryption, right? And when you do your decryption, just like any other asymmetric algorithm, you then use your private key. So, if you ask me, I will say the RSA is 3 stages. Stage 1 is the key generation. Stage 2 is encryption. And stage 3 is decryption. Now, stage 2 and stage 3 are just straightforward. You just do encryption using the equation that you're given. Stage 3, the same. You've got your equation for decryption. But stage 1 has 5 steps. Now, the first step, when you are encrypting a message, right, is to generate 2 large numbers. What are the numbers or you can say choose two large numbers. You can generate them, you can choose two large numbers, and they have to be prime. Prime, why? Because when you secure your system using, like I said earlier on when we were discussing what is needed when you do for you to implement a sound cryptanalysis or crypto system, I said you need to know the properties of numbers. Very, very important, especially when it comes to integers and prime numbers. Now, it's going to be difficult for someone to just try to come up with a combination of those two numbers, especially if they are prime numbers. Which two prime numbers? That's the golden question. So it's difficult for someone to assume, especially if you are to use very, very big prime numbers, large prime numbers. So your prime numbers, we denote them with P and Q. Then step 2 is to compute for the totient. No, not for the totient. Is to compute for the modulus of the numbers. In other words, we're saying calculate n. How do you find your n? N is equivalent to P multiplied by Q. Right? That is your second step. You need to compute for P and for n, which is given by P and Q. In any case, isn't it you are giving you generated your, or you computed for your P and Q? So it's now very, very easy for you to just compute for n because you already have the two numbers which are required. Third stage there is to compute for the totient. Right? Now, the totient, again, you are deriving it from the variables that you already have, because totient, which we normally represent with phi, with a phi, n is equivalent to P minus 1 and then Q minus 1. So you computed your P and you computed your Q. So it mustn't be difficult for you to calculate your totient because you already have the numbers there. P minus 1, Q minus 1. Then you're good. Then stage number 4, we are still on the first step, that is key generation. The step number 4 is to compute or to select or to choose a random number. Choose a random number. That random number, we are going to perceive it as our public key, right? Here. That's where we have, sorry, let me use a different color. This is where we have our public key. And the public key is denoted by the letter E, right? But there are two things which you need to observe here. Two conditions which are essential when you are selecting your E. Condition number 1 for your E, for your public key, you need to have your E in between, that is your E must be greater than 1 but less than your totient. Right? That is the first condition. The second condition, the GCD of your E and your totient, right, must be equal to 1. In other words, the value of E and the totient mustn't have any other factor save for 1, right? In other words, someone will say E and if totient and your totient must be co-primes. They don't have any other factor. Then the first condition, like I said, it has to be in between the value between 1 and the value of your totient. This is stage number 4 for E. Then the last step on your key generation is to calculate your D, or you compute for D. This one you are calculating because you don't need to generate it. You are calculating based on the information that you have. But of greater importance here, is for you to acknowledge, right? is for you to acknowledge the fact that the formula that you use when you want to compute for day is, we have got DE, it's DE, it's DE is equal to mod n, if I'm not mistaken. I think DE is equal to mod n, yes. But the idea now is to make D the subject of the formula. So when you do your computations properly, your D must be equivalent to 1 plus a constant that is going to emerge. Here it should be phi mod n. Yeah, phi mod n. You verify that. We will verify that anyway. So I was saying, no, there is a 1 plus. Okay, let me correct myself here. I'm saying DE, I just remembered something, is equal to 1 plus mod phi n, right? So if you try to simplify this equation and make D the subject of the formula, you will remain with 1 plus a phi n, right, over E, because you're making D the subject of the formula. This formula is very, very important, right? This is a stage where you were supposed to use the extended Euclidean algorithm, but it's so tiresome. I believe it's slightly long. So you can actually use this shorter method. How are you going to do it? You now need to say, my k is a constant and I want to iterate it from 0, 1, 2, 3, 4, until such a time I get the value which, give me an output of D as an integer value, right? Not as a decimal, but an integer without a remainder. Oh, you appreciate it better when you do the calculation after this slide, right? This is how you are going to calculate your private key. And your private key is denoted by D. The public key, we can actually denote it with EN, right? With EN. This is your public key. And your public key, you can even publish it. It doesn't matter. But private key, you keep it, right? You keep it. You keep your private key. Then when you are done with the first step of our RSA. The second step is to do encryption, where you are going to use the formula C is equal to ME mod N. C, why encryption? Normally you are encrypting to get the ciphertext. So ciphertext is denoted by the letter C. Then M. M is used to denote the main message or the plain text or the original message. Then you raise the original message to a power of E. E being the public key, right? You have already generated the public key. Then mod N, of course, you'll be having your N. Then you do the computation for encryption. Then when you decrypt this very message, you now need, what is the end game for decrypting? You need to get the original message. So the original message is equivalent to M, and you do that by making use of the ciphertext, right? Which is represented by the letter C, and you raise it to a power of D. D being the private key, right? Then mod N. That's the RSA algorithm. And I can sense that maybe it's difficult for some of us to appreciate this. But now, let's try to have an example, right? Let's try to have an example and see if people are getting the message. If they're not getting the message, then we'll try to find other ways. The first stage, or the first step, like I indicated, is part of our key generation. So this is all part of key generation. This is all part of key generation, right? These are the 5 steps that you need to follow when you do your key generation. So your P is like the first step is generate two numbers, P and Q. We now have our 5 and our 11. Then the second step is to compute for N, which is 5 times 11, and you get 55. Then you calculate the totient phi of N, which is equal to P minus 1, 5 minus 1, which is 4. Then Q minus 1, 11 minus 1, which is 10, and you get 40. Right? So far so good. Then the fourth stage was to select a number which is between 1, the value of E, isn't it, the public key, and 40. Right? This is the number that we need to generate. That was the first condition. And also the GCD of our E, the number that we're trying to generate, and 40 must be 1. The number that we need to generate and 40 mustn't have any other factor except 1. So, and you are selecting a prime number, by the way. This is supposed to be a prime number that you are selecting. So, prime numbers, we've got 2, we've got 3, we've got 5, 5. You've got 7, 9 is not a prime number. Then 11 is 13, 17, 19, 23, 29, going like that. That is the order that you follow when you want to select your prime numbers. Now, the algorithm, listen to me, practically, the algorithm will be very, very strong if the value of P is very, very large. The value of Q also being very, very large. The number E that you're generating being any random number, or even if it's larger, it becomes even stronger. But for academic purposes, if we deal with large numbers, your calculators won't be able to compute. So we limit ourselves to the theoretical aspects by using small numbers. So generate a small value of E. One would choose maybe 2. You cannot choose 2 here, because 2 and 40, you have got what? Have got many other factors, isn't it? They are not they are not co-factors. They've got other factors, right? In any case, we say we want the factor that we're generating and 40 to have only 1 as a common divider. So I selected, within the context of my example, I selected 7. Right, because E satisfies the both conditions. E7 is in between 1 and 40. 7 and 40 also don't have any other factor except 1. Right? So I'm done with my what? With my encryption. So my public key, I can say the public key is equal to EN, which is 7 and 55. That is my public key, right? And you can publish that, it doesn't matter. Then the one which you need to keep private is the private key, which you're going to use for decryption. And I gave you the formula D is equal to 1 plus phi n all over 40, all over E. So I'll then try to use the variables that I have here. 1 plus, what is our value of phi? That is 40, right? All over, what is the value of E? The value of E, I think we indicated that it's 7. Now, 40k rather. Oh, here there is a k, isn't it? Right? There is a k. You need to put a k there, otherwise it's going to be difficult. K is the constant which we generate when we remove, the mod and all those things, right? So now you need to iterate from k is equal to 0, 1, 2, 3, 4, 5, until we get a whole number. Now let's do it together, right? Let's do it together so that at least we'll appreciate. Now, if k is equal to 0, this becomes 0. So we have 1 over 7. 1 over 7 gives us It doesn't give us a whole number, isn't it? 1/7 gives us a decimal number. We don't want a decimal number, right? 1/7 is 0.14 something, something, something. So this is out. You iterate. If your k is now equal to 1, 1 plus 40 times 1, that's 40. 41/7, it's also a decimal number, 5.8 something. It's out. If your k is equal to 40 times 2, it's 80, plus 181/7. It gives us 11 point something. This is out. If your k is equal to 3, if you put 3 here, it becomes 40 times 3, 120, plus 1, 121/7. You also get 17.2 something, so your 3 is out. If your k is equal to 4, you put 4 here, 40 times 4, that's 160, plus 1, 161/7, it's equal to 23, which is a whole number. So this 7 gives us a whole number. What is the whole number? It's 23 for the whole function. So 23 becomes our private key. 23 becomes our private key, and we keep that private key because that is the number that we're going to use for decryption later on. Now, going forward now, we are now going, this was stage 1, right? This was stage 1. Now we go to stage 2, where we need to use the form to do the encryption, and we encrypt by using the formula C is equal to m to the power e mod n. And you've got your message here, the message that we are given. Let's say you are being asked to encrypt 30. 30 being the message, you raise it to the power e, which is 7, isn't it? We computed for e here, right? Then mod 55. Right. 30 to the power 7 mod 55. I don't know if you enter in your calculator doesn't have the mod function. Or should I say, the calculator that is expected within the exam mustn't have the mod function, right? So if you say 30, 30 to the power 7, where is this function? Okay, I need to put it on this. 30 to the power 7, right? It gives you a very, very crazy number. So what are you supposed to do? I always tell my students, I have got many ways of doing this, but I think you now need to write your 30 to the power 7 as a product of its what? Indices. You can say 30 is equal to 1 plus 2 plus 4, right? Then you still have your mod 55. Are you following? For you to get 30 to the power 7, you can say 1 plus 2 plus 4, right? This power is still equivalent to that. So what you need to do now is to calculate the modulus of 30 to the power 1 mod 55. Then calculate the modulus of 30 to the power 2 mod 55. Then 30 to the power 4 mod 55. Then 30 mod 55 is just like it's just like I said 30 to the power 1 mod 55. It's equivalent to 30 mod 55. So what you do, if you enter in your calculator, I'm sure you get a number like 30, right? This is equivalent to 30. Oh, sorry. 30 is here. This one is not supposed to be there. Then 30 squared mod 55. You also enter it in your calculator. 30 squared. How do you calculate the mod, by the way? You say 30 for the first one. 30 divided by 55. Mind you, we are worried about the what? About the remainder, the quotient. So 30 over 55, you get 0.5454. Focus on the remainder, the decimal part rather, right? Which is 0.545. Then multiply that by 55 again. I'm sure it will come back to 30. The same applies to 30 squared. 30 squared, it's 900, right? Divided by 55, you get 16.3636363. Focus on the decimal part. 0.3636 or 0.364, right? 0.364, multiply it again by 55, I'm sure you get a 20. Then 30 to the power 4, you can enter this in your calculator. 30 to the power 4, which is 810,000. Divide this by 55 and focus on the decimal, which is 28, I think. 280, 280, right? Then the decimal part, 0.280, multiply it by 55. You get 15, right? 15. So that being the case now, with your 15, you can safely say, okay, am I doing the right thing here? I hope so. I hope so. We selected our ES7 and our value for D was 23, which is okay. The message is now 30, and 30 to the power 7 mod 55. Then we did this. This is not much of an issue. Okay, you could enter this in the calculator, but I'm dealing with situations whereby you might have bigger powers, so you need to grasp the concept. Now, you multiply your 30 times 20 times 15. 30 times 20 times 15, right? And divide this over 55. Then you will get 0.63. Let me confirm something.